This is what, the second theory session on chapter 18 on homomorphisms. Again, quite a bit of tight logical reasoning. Once again, I'm doing an experiment. I noticed in the previous session that the background traffic noise on the road about 50 meters in that direction, because I'm recording this in the bedroom where the lighting is softer, so less damage to my eyes. So given that background traffic noise just didn't seem to be picked up, so I assume that the microphone, the inbuilt microphone in the camcorder, the Handycam, is highly forward directional. So I'm hoping that the sideways sound of the air conditioning machine, which I'm having on right now, because it's damn hot now. It's late June in southeast China, in the city of Xiamen. It's hot. So if with this experiment, when I play back the results of this recording, if I hear no sound, no trace of the noise of the air conditioning machine, then I will continue to have the machine running while I'm recording in more clothes, because I'm on camera. Normally I strip down to undershirt, shorts. Okay. Well, we've been doing a string of examples on homomorphisms, and the chapter has 8 of them, and I think this is the last one. So we'll talk a bit about that, and then finally introduce you to the concept I've been hinting at quite strongly several times in the previous session. So here's the critical word, and then do some theory on the basis of this, and next chapter, the final chapter, chapter 19, lecture 19, we'll use this concept as the basis, the main idea of the chapter. Alright, so let's do yet another example of a homomorphism. What we're doing this time is just taking a group G, and we're using a mapping function f to map that group, just any old group, into well, you can just see here, it's with a division sign. This is a quotient group. Okay, so did a whole chapter on quotient groups. The previous one, lecture, what would that have been? 70. Right? We're now lecture chapter 80. All right. So this is a quotient group, and so you're mapping from a group into a quotient group. So larger group into a smaller one, and the function f is defined for an individual element x belonging to G in this form. So you know that a quotient group consists of what? Cosets, right? So this function here will map just some element x into some kind, one of the cosets of this quotient group, right? So let it be xn. So define your function f so that f of x is xn, right? And we can now show pretty readily, in just a line of proof, pretty simple, that this particular function that maps x into xn, where n is a normal subgroup, okay, of G, we can show pretty readily that that's actually a homomorphism, right? And how do you prove anything as a homomorphism? By f of mn equals f of m times f of n. Okay, the usual, this stuff. Well, x, y instead of mn. All right. So we have to show this sort of form. So let x and y just be any two elements of your group G. All right. So well, let's start with the right-hand side and try to prove it's equal to the left-hand side. So for any two elements of G, x and y, so f of x, f of y, here it is here, equals what? Well, we just use this definition, right? So f of x is xn, that's where this comes from, and f of y is f of y will be yn, so put that in here. Now, remember from the previous lecture, what are you doing here? Well, this is a coset, right? So is this. So we're binding operating, multiplying in a sense, on two cosets. And how do you do that? Well, you use what I called subset multiplication, right? And you probably remember from the theory of quotient groups that when you multiply two cosets, this becomes this, right? So you can rewrite this as this. But what is this, right? X, Y, then. Well, just use this. So you've got an xy here, so this will just be f of xy, right? Alright, so therefore this equals this, and there's your proof that f is homomorphic. Right? Now, in quite a few of these examples of homomorphisms, these functions that obey this property, that this is equal to this, it's the definition of homomorphism. The textbook's been asking the question, what under a given homomorphic function f, which elements from your g, you start with g and you map to h, which elements map to the unit of your h, like e of little h. This little point here in a Venn diagram represents the unit element of this group H. Okay, so the question here is, well, firstly, what's the unit of this? Right, this quotient group. What's its unit? And then it asks what elements in your G map to the unit of H. And we've been asking this question consistently because we're using that question as a kind of a lead-in to the introduction to a new concept called, well, I won't even mention it yet because it's not quite there. All right. So for this quotient group, what is its unit? Right? It's a group. Every group has a unit. So this quotient group, what is its unit? Well, it's e to the n, which is just n. Right? We talked about that earlier. Right? So the unit of a quotient group of this form is just en, right? Which is just n. So the set of elements belonging to n, the normal subgroup, that set, coset, because E times the set is a coset, so that n is the unit of this, right? Okay, now as a bit of a tangent, this is a reminder of Theorem 46. Again, we're using this famous Theorem 46 quite a lot. It's a very useful theorem for a lot of material that's followed. I mean, I keep referring to this theorem, either the first part of 46 or the second part, this time using the first part of 46, right? So it's just a reminder because we're about to use it. Okay, so what does the first part of Theorem 46 say? It says if you have two cosets equal, if two cosets are equal, like x of n equals y of n, x and y are just arbitrary elements of your group G, right? So if xn equals yn, well, sorry, xn equals yn if and only if x inverse y belongs to n, right? So if this is true, that's true. If this is true, that's true. It's if and only if, both ways. Okay, all right. Now it's any x and any y, so let's choose x to be the unit of G. So e little g. So suffix g, right? So x is the unit of G. Well, in that case, you'll just have n here. So n is yn. You've written it there, and this x is the unit. so the inverse is still the unit, so the unit y is just y, so you can rewrite this as this. Okay? So if you're using the x as the unit, then n equals yn implies that y belongs to n. Now remember, these two, they're both ways. It's if and only if. Each direction is valid. Each direction is true. Right? So we're going to use from this to this one in this case. So if n equals yn, then y here belongs to n. Right? Now you may say, well, what's the point of talking about all this? I'm going to use it to answer this question. So this is a kind of reminder with a little bit of deduction of previous theorem, because we're about to use it. Okay. Now we keep asking this question: what elements from G map to the unit of H? Okay. So for this problem, this exercise, this example, let's ask the same question. What elements of G here map to the unit of your H? The group that you map to. In this case, it's the quotient group G slash n. All right.